we've finally got to the objects that we're interested in this course, namely symplectic manifolds, and also the maps between them, symplectomorphisms. But we don't really have a connection to the kinds of systems that we encounter in classical mechanics and beyond, and this abstract formalism that we've been building. So in the coming lectures, we're going to take a look at a way to construct symplectomorphisms from things called vector fields. And where are we going to get these vector fields from? We're going to get them from Hamiltonians. So what we need to do is find a way to fit within this differential geometry framework the language of Hamiltonians and the Hamilton's equations in a way which gives us vector fields and which connects with symplectic manifolds. So that's the objective for the next couple of lectures. And to do that, we'll have to spend a little bit of time talking about vector fields, what they are, and things called flows, which is what happens when you integrate a vector field, and then differentiation with respect to these vectors, which we'll see in the next lecture, I think, or this lecture, called Lie derivatives. So, to remind you, what's a vector field? Well, it's a choice of a vector in the tangent space to the manifold at a point x for every x. And this is smooth. Unless I indicate otherwise, this choice is a smooth choice throughout this course. We don't allow discontinuous vector fields except where I tell you. That's a vector field. Now, we're going to introduce a notion of an integral curve for a vector field. So exploiting, if you think about a vector field as a bunch of little arrows on the top of a surface, draw a little cartoon here. Here's the sphere, for example. And a vector field is like an assignment of vectors on the sphere here, one per point on the sphere. You could imagine that there's a curve that goes through and is exactly tangent to all the vectors along this curve's trajectory. Such a curve is called an integral curve, and it plays a very important role in Hamilton's equations, Hamiltonian dynamics. Yep. Is there a difference between a section of the tangent bundle and... There's no difference between a section of a tangent bundle and this, but I don't want to use the sophisticated language of tangent bundles. So let's give a name to this idea of a curve which is tangent to which has the vector field tangent to it at each point along the curve. It's called an integral curve. Little x of t. Well, what is an integral curve? It's a curve. It's a kind of curve that's special. And what's the special property that it has? Well, the tangent vector to the curve at the point little x of t is exactly big X. Such that its tangent vector so given a vector field X on our manifold, our objective now is to work out an integral curve, is to find the equations that an integral curve need to satisfy, and then try and solve those equations. So to do so, we go to a chart, we use coordinates. If you ever want to actually calculate something, it's vital that you actually have coordinates. So we imagine we have some given to us by some chart. This condition that the tangent vector to the curve at the point x of t is big X at the point x of t can be written in coordinates in a very simple way. Given by this equation in coordinates. So these capital X mu are some perhaps nonlinear functions of the coordinates x mu. So that's the explanation for the symbols here. They're just the coordinates of this curve. These are the coefficients, yes?
And isn't it possible that if you have a manifold with a boundary, that we can leave the manifold?
Oh, yeah. Isn't it possible if we have a manifold with a boundary, we can leave the boundary? It sure is. At the moment, this definition is only for manifolds without boundary. So at the beginning of this course, I believe I made, or I should have made the comment that we won't deal with manifolds with boundary unless otherwise specified. Yeah, if you don't want it to leave the manifold, you have to have extra conditions on the vector field.
Would this be explained on the boundary? Because if I think of the definition, there can't be a curve going through the point that is not tangent to the boundary. Manifold.
Okay, the observation is that wouldn't this actually be explained on the boundary because tangent vectors to the boundary have to be literally tangent to the boundary. Actually, I think you're still in for problems. Just think of the interval. So the simplest example of a manifold with boundary is the interval, or even the half line, right? I'm not completely convinced that that vector field there, which is smoothly goes to 0,
Maybe you have to specify the t interval to say that we don't have the possibility to go further than some t.
yeah. Short answer is I don't know. I don't know if on manifolds with boundary, if you can leave or not leave according to this definition, the boundary. It still makes sense to talk about an integral curve, however. You have a vector field, you have a curve, it's tangent everywhere to the curve. Whether or not that trajectory leaves in finite time the boundary is, at this point, for me, a little bit unclear. I don't know the quick answer to that. However, we're going to restrict to manifolds without boundary for a long time, possibly the rest of this course. And we won't have to deal with such complexities. Yes. So if we've got a vector field, if we specified it somehow in coordinates, then it's reasonable to ask, can we find an integral curve? This is very much related to the discussion we've just been having. In fact, we have more worries than boundaries. So it might be that given the vector field x, that a solution, an integral curve, does not even exist for all time. So given x, what we have to do to get the integral curve is to solve this system of ODEs. And the question of the existence of an integral curve, finding an integral curve, then becomes equivalent to the task of can we integrate a system of ODEs? Does there exist a solution to that system of ODEs? Is that solution unique? And does it exist for all time? So we can give partial answer to this in the case of non-compact manifolds, and a pretty complete answer in the case of compact manifolds without boundary. Actually, I'm inclined now that I think about it, to say that with boundary, it's not going to work, because I believe we could set up systems of ODEs where the solution has a finite time blow up. So I think the answer is with boundary, the solution can escape, but I won't commit to that. Just say I think. So when will I talk about that? later. Okay, I'll talk about existence and uniqueness presently. This is something that I hope you've encountered, at least heard the words, existence and uniqueness for a system of ODEs, Picard existence theorem. These are words that at least I hope you can look up. And you should be aware that there exists a finite interval of t where you're guaranteed to have a solution, and that solution is guaranteed to be unique for this initial value problem. I haven't given you the initial value, I will presently. And you should also be aware that there's a theorem that tells you if you have a compact manifold that the solution to a system of ODEs not only exists for a finite interval of time, in fact exists for all time. The integral curves exist on compact manifolds. So these are all theorems that I'm not going to cover in this course, I'm just going to invoke them. The proofs involve the fixed point theorem. In some sense they're relatively elementary, but I won't cover them in this course. So to find an integral curve we need to solve some ODEs. And the nice thing about ODEs is you can just stick them in Runge Kura in your favorite mathematical program and it will just plot the answer. It's fantastic. So let's make some observations about integral curves. And these observations are to do with giving the ODEs here enough data to be solved. This is not yet an initial value problem as written here. I don't have an initial value for these ODEs to integrate from. However, if we demand further that the integral curve passes through a given point that you like at time t equals 0, then we have an initial value problem for these ordinary differential equations here, and we can go ahead and solve that numerically. And we're going to give that solution, sigma t, sigma, the name sigma, and it depends on two things now, doesn't it? It depends on time, and it also depends on the initial value that you chose to put into these ODEs. And let's just make some observations about these integral curves. So this is a function of two arguments, t and x, and it gives you a point in the manifold. We're going to give this thing a name in a minute. It's going to be called the flow of the vector field x. It's the terminology we're going to use. Coordinates. Then the equation, these ODEs here, in terms of the coordinates of sigma, are written very simply I'm just rewriting out this system of ordinary differential equations here with subject to sigma mu at t equals 0 equals x0, the coordinates. So now we have the data of an initial value problem. Go ahead and integrate. So let's give this thing a name. I've already said it, but let's write it out. So this function that goes from r cross m to back to m, sigma, this is something we call the flow, or a flow. Now, a flow satisfies a really remarkable property that we're going to actually prove, namely that if you flow on from some other point that you flowed to first, then that's the same as flowing for the same time but from the original point. So we're going to prove this in a second. So let's prove the boxed statement. Well, what we're going to do is just differentiate it with respect to t, with respect to t plus s, and check that they both satisfy the same equation. Okay, it's the equation of motion satisfied by the left-hand side with subject to the initial condition that at 0 we get sigma s x naught. What about the right-hand side? This is the left-hand side. Right-hand side. Well, we have to differentiate it. We want to get an equation of motion for the right-hand side, and we can do so. First, we just differentiate the right-hand side with respect to t, but then we notice that, well, that's the same as differentiating with respect to t plus s. Can shift our differentiation variable. And then, again, we know the equation of motion satisfied by that thing. And that's subject to the initial condition that 0 plus s x naught is indeed s x naught. So if we call this thing here little f of t, and we call this thing here, where have I written it? Little g of t, right? These are potentially different functions from r cross m to m. I'll put the mu in here so it's clear that they're really a vector. Then what you've got, what we want to do now is show that f of mu equals g of mu. And just notice the strikingly simple fact that f of mu and g of mu satisfy the same ordinary differential equation initial value problem. And so there exists an interval minus epsilon epsilon with t in it, such that the solution to star exists and is unique. That's what the existence uniqueness theorem of ordinary differential equations tells us. There's an open interval, non-empty interval of time such that the solution to these equations exists, and furthermore, it doesn't just exist, it's unique. If you have two solutions, they must be the same. And so at least for an interval minus epsilon to epsilon, we learn that sigma mu t sigma s x naught is exactly the same thing as sigma mu t plus s x naught. Now that's the best you can hope for in general. The existence uniqueness theorem, there are counterexamples for extending the domain of uniqueness beyond some interval, and particularly in the case of non-compact domain manifolds. However, in the compact case, things are even better. So I didn't put the domain of time around which this is actually a valid statement. So what I should have said is there exists epsilon bigger than 0 such that the flow satisfies blah for all t in this open interval there. So what can go wrong when you try and extend the domain T is that you can have finite time blow-ups in nonlinear equation. It's possible for nonlinear ordinary differential equations on a non-compact target space to have a finite time blow-up, that they can in a finite time reach infinity. It's very possible. And let's see if I can't remember the equation that does that. I think it's dx dt equals 1 over 1 minus x. So I think that has a finite time blow-up. Yeah, it does, doesn't it? If you integrate that thing, you get something like some square roots. That's an exercise. So if that's not an example, then your exercise is to find an example which does have a finite time blow up. But why does it blow up? It blows up, the solution the solution fails to exist because x is allowed to go to infinity. There's no bound on how big x is. But if the target space that x is allowed to visit, if that's not this non-compact real line, but in fact a compact manifold, then it turns out you can extend the domain of definition for this unique solution for all time. So that's a relatively elementary consequence of the Picard existence and uniqueness theorem, although it is profounder. All right, so we've shown that the flow satisfies this property here. Looks like a semi-group property, right? Do something, then do something else is the same as do those two things. Semi-groups are good. We like them. We in particular like groups even more, but we'll take a semi-group when we're given one. So we're going to summarize all this in a theorem. So for any point x in a manifold M, there exists a differentiable function sigma r going from r cross M to M such that at time t is 0, sigma naught comma x is just x, so it has the right initial condition. And t mapping to sigma t comma x satisfies the integral curve equation star. And finally, it has this semigroup property. Well, should be a bit careful with using the word semigroup even. Because it's not really a semigroup, because there can exist a finite t where this thing blows up when M is not compact. And so far we're being a bit woolly whether or not M is compact or not. And will I make it compact now or wait a bit? Let's see.
Otherwise there would have to be a restriction.
There has to be a restriction on t, yeah. Okay. I kind of like not want to make this compact just yet. So let's put that restriction on t. And then I'll say there exists an epsilon greater than 0. And then, yeah. And then add this in as a kind of remark. If the manifold is compact, then epsilon can be taken to be infinity, namely the real line. So these existence and uniqueness statements may seem pretty mathematical. Like, you know, in physics, we know when the solution exists, right? Well, in classical mechanics, these are deep physical questions tied up with existence and uniqueness. So when the equations of motion you have are nonlinear, there's certainly no guarantee that in finite time you don't have a runaway solution that goes to infinity. And certainly just for a couple of variables, we have a pretty good handle on when this is going to happen in some physical system. Now, a situation where things are much less clear is partial differential equations, which, if you like, are just an infinite number of ODEs. So essentially, sort of morally, that's the same thing. There, the situation is absolutely unclear, and there's deep physical reasons for wanting to know about existence and uniqueness of solutions. So the classical example is the Navier-Stokes equation. So it's a nonlinear set of partial differential equations. And you might want to integrate that set of equations to find out what the fluid will do in a couple of minutes. So then you might wonder, well, is it possible that this set of equations has a solution in a couple of minutes? And the answer is nobody actually knows. Right? At the moment, that's a big open problem, whether given some initial data, which is this stuff here, whether or not the solution to Navier-Stokes equation exists for all time, or it can exhibit a finite time blow-up. And there, somehow physically, we know what the origin of such a blow-up might be. It's the fact that there's turbulence and that there's motion at all length scales, and that these can somehow contribute to each other to make the solution kind of rupture. So we don't actually know for Navier-Stokes. It's an actual physical system where these questions are quite pertinent. There's some toy models of Navier-Stokes equations, which are systems of ODEs, still an infinite system of ODEs. They're a nonlinear kind of discretization where indeed it's known that for a finite epsilon, this discrete fluid will blow up in a finite time. I won't say anything more about that, except to point out that, yeah, existence and uniqueness is physically interesting as well. Okay, there's a special class of flows that we're going to come back to occasionally. It's called isotopies. So suppose we have some kind of flow for some vector field x. We'll just say a flow. I won't tell you what the vector field is. Then we're going to give a special name to this flow if it has a certain property. So first of all, let's just set some notation. We often do this, that the time argument here is somehow more convenient to put as a subscript. So suppose our flow is a nice one, not a bad one, but a good one. Let's say exactly what good means. Then we're going to give it a name. It's called an isotopy. An isotopy if this map here is a diffeomorphism for all t. So obviously that means it's got to exist for all t. And when t is naught, this thing is the identity. The do nothing map. Okay. So my notes are written for the compact case all throughout, but I don't like sort of restricting to that necessarily. So actually, come to think of it, I believe we can still get away with this for the non-compact case. I think this definition makes sense also for the non-compact case as well. Just, you've got to bear in mind that when the solution exists, it's a diffeomorphism. Yeah. Isotopies, very important flows. Isotopies turn up in all kinds of places. And are the natural notion of equivalence for knots. So if you have two knots written on the plane with over and under crossings to indicate whether the string is on top or underneath, then you want to say when two knots are equivalent. When are these the same knot? And the important notion of equality in the category of knots is that of isotopy. So you should be allowed to smoothly deform knots one into the other. So this sigma t here is like the movie. You watch the movie of the motion, and it's a diffeomorphic. It's a nice smooth map for all t's. You can see it as time runs forward, deforming and undeforming the trajectory. Now, given an isotopy, we can always find the vector field which gave rise to it. So notice before when I defined the flow, I had in mind a static vector field. Now, given an isotopy, we're going to be able to find a vector field, possibly time dependent, for which sigma t is kind of like a flow. And it's pretty simple, right? Given that you're interpreting an isotopy, which is a map such that sigma t is a diffeomorphism, as a flow, well, it's kind of natural to differentiate with respect to S, isn't it? So define this vector. That's how we get our vector field, our kind of effective vector field for an isotopy. So all flows are isotopies, but not all isotopies are flows. And we see that this satisfies the equation of motion for an integral curve, but now with respect to a time-dependent vector field, V. So at every flow there's a time-dependent vector field which gives rise to it upon integrating this equation of motion. Now we're going to argue the opposite. We're going to say, given a time-dependent vector field, we get an isotopy. So then we can draw a one-to-one correspondence between time-dependent vector fields and isotopies, which is pretty neat. This is only going to work in the compact case. You're in for real trouble if you want to look at time-dependent vector fields on non-compact manifolds, because they don't have a notion of energy conservation, and you can be pumping energy into the system, and the trajectories can go crazy. So, yeah, for example, think of the pendulum, the kicked pendulum. That's a system where the vector field is time dependent. I mean, it has a delta function, but whatever. And you can have extremely chaotic behavior. Oops. Conversely, given a time-dependent vector field V, depending on time, and now I'll say it clearly, if M is compact, so kicked pendulum is a reasonable example. Kind of half example because the configuration space is compact, but the tangent bundle to the circle is not. It's a cylinder. So, and if M is compact, then we have a one-to-one correspondence between isotopies of M and time-dependent vector fields. Oh, yeah. So when, I mean, this is slightly deceptive, this observation here, because things can be really complicated even on compact manifolds, even on really simple compact manifolds. So the example I want to highlight is what happens if you're on a torus. So torus is just really the square where you identify opposite edges. And I want to think about the vector field where it's this uniform vector field. It's the simplest vector field imaginable, where this vector has, say, it's a time-independent vector field even. I mean, how easy can this get, right? It's going to be 1 and 1 plus root 5 over 2. So let's just look at the integral curve to this vector field with initial condition t is 0. What we get, well, we get some real crazy stuff happening. So you draw your curve, and you know how to integrate this equation of motion, I hope. It's just a line up to the top of the torus. So this torus has height 1 and width 1. And when it hits the top of the torus, well, that point's the same as this point. So that one comes up here. And that point's the same as this point. Up to the same as this one. Blah, blah, blah. And if you keep following this curve, then you get a foliation of this surface by this one-dimensional weird embedded integral curve here. And these things are extraordinarily strangely behaving as a function of the initial condition. So one is sort of looking at something like this, one is tempted to think, well, you know, this is obviously really, in the compact case, everything's super nice. Well, the answer is even a particle with no external forces, but with an initial momentum kick, even that kind of example can lead to extraordinarily complex behavior. When you decompose this surface, the torus is a union of these curves here. It's very, very complicated. So you take an arbitrary point in here, and the curve gets arbitrarily close to any point, but at very strange times. So the time where this curve gets close to that point depends in a very complicated way on t and t times the golden ratio here. That's the golden ratio phi. So if you have a point x, y in the manifold and you ask, when does this integral curve get close to it? Well, then you're trying to solve this equation, right? When is that close to that? And that's pretty complicated. Especially when y is a rational number. So we have, oh yeah, I forgot the modulo condition, right? This is all modulo the square or the torus. I mean, obviously that's easy to solve, but if you have to identify x is equivalent to x plus 1 and y is equivalent to y plus 1, now you got yourself an interesting problem on your hands. All right, so that's sort of a warning, if you like. Interesting dynamical systems. In particular, that particular system there is quite a nice example of something which we're going to give a name to. So when this vector field is independent of time, then we're going to give this thing this isotopy a name, right? It's the flow. But it's also, we know a lot more about this flow. We can give it a special name. It's called the exponential map. And that's because we know a lot more about the structure of sigma in this case. So this is some notation here. So this is a bunch of diffeomorphisms, and they satisfy some equation. Well, what equation? Well, at time t is 0, by per definition, that's the identity. And if you differentiate this isotopy here with respect to t, well, you just get x. Now, you know, when you introduce a notation like this for something, you do so for a reason, and that's to imply or intimate some structure. So this is sigma t, right? I've just written sigma t in a funny notation with this exp. Now we've chosen the notation exp because you can express sigma t really as a Taylor series which looks exactly like the exponential. So let's justify this. Should only ever change notation if it helps compactify what you're doing, so give you a more economical way to represent the same thing. It's a valid reason to introduce notations. Reduce the surface area of things you have to remember. Or the other way, the other reason you might introduce a new notation is because you want it to be helpful to notice a property about a thing. And that's what we're going to do now. So what we're going to do is look at the flow or the coordinates of a point that's been flowed for a time t with respect to a constant vector field. Now, we're going to exploit a Taylor series to just look at this at powers of t. So at time t is 0, it better be the initial condition, x mu. And then at time, at first order, we have to take the derivative of our flow, set s to 0, and then multiply it by t. This is just the first order term in the expansion. And then you get some higher order terms, and all is well. It's just the Taylor series. And I'm not sure if you've seen this before, but a neat way to remember the Taylor series expansion is just notice that it's the same as the Taylor series of e to the t times ds. At s equals naught. Have you seen this trick before? That's the identity operator, e to the t to the ds at s is 0. Okay, that's just a neat way to remember a Taylor series. But another neat thing is that d ds of sigma mu has a name, right? It's capital X. So in place of all these d ds's, we could put capital X's. So it's actually equal to e to the t capital X. So that's why we can justify the notation. Okay, let's summarize all the things we've observed about our flows, and then we can move on to defining some nice operations with flows. So this exponential map flow sigma t satisfies some properties. First is that the one we've already seen, isotopy condition. The second one is that the derivative with respect to t of sigma t obeys this equation. Is just the exponential equation. And we furthermore have a proper group property. So we're all in the compact manifold case now. So if you flow for a bit and you flow for a bit again, then that's the same as flowing for a bit and a bit again. But that's the same as two exponentials like this, which is the same as e to the s plus t, now for all time. So since this is for all time, that makes this into a group, a one-parameter group. Of diffeomorphisms. that was a brief reminder of these things called flows, isotopies, and the exponential map. All these things will appear throughout the rest of this course. Now we come to the topic of how to introduce derivatives of vector fields and things like that. So the problem with manifolds, in contrast to the real numbers, which is what we model a manifold on, is that when you want to compare two things at different points, it's not quite clear what compare means. So if you have a point here and you have something at x, be it a vector, be it a one form, be it a tensor, and you have another point on your manifold over here, y, and you have another vector over there, a tensor or a one form, how can you meaningfully compare those two things, right? So if I have a vector here and a vector here, how can we take, say, the difference of these two things, or the sum, or anything like that? The answer is you can't, right? At this level of information, what I've handed you here, there's no canonical recipe for how to compare, say, two vectors at different points on a manifold, which is not flat space. I mean, if you think about flat space, you do have a way to compare a vector at 2 points, x and y. The way you would take the difference of these two vectors is you would just drag this vector over to here, so its base point is the same as this one, and then just take the difference. That's how you could take the difference of two vectors in real space. And you're happy that that's a well-defined recipe, because if on Tuesday you drag it this way and on Monday you drag it this way, you're still going to get the same answer. Doesn't matter how you drag that vector around, you're always going to get the same answer when you compare the two vectors. So that's obviously canonical, and that's an obviously correct way of taking the difference. However, as you're well aware from your experience with general relativity, if you try this out on a manifold with some kind of curvature, you're in for trouble. In fact, even on planet Earth, you're in for trouble. Right? You go to the North Pole and you compare a vector at the North Pole with a vector here, then if you're kind of dragging this vector parallel to itself all along your path, you can end up with two different answers. So, until you can come up with the ludicrous situation that if you compare a vector to itself, you can get different answers depending on the path you took the vector around. So if you have a vector here at the North Pole, and you take this vector for a little walk along this longitude here, so you take the vector for a walk here, and then you take the vector for a walk here, and then you bring the vector back, then you get, what? It's a different vector. So this actually happens, right? You can do this experiment if you want yourself. Even here in Hanover, I think there's just enough curvature that we can have some interesting answers. If you went for a little walk with a vector, keeping it parallel, and then you come back to where you started, then the vector's a different vector. So like, what? So you can't, this prevents you from canonically taking the difference of two tangent vectors. And this also extends to one forms and tensors and blah, 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 blah. So this, of course, this problem is well known to you. And the only way to solve it is you just need more information. There's not, if you're just told this, that you've got two vectors on a manifold, then you're more or less cooked. There is no canonical recipe for how to compare two vectors. However, there's ways out of this problem. The first way, which you're no doubt familiar with, is in Riemannian geometry. We do have a sense of parallel transport. What's the correct way to move a vector along parallel to itself? There we get an answer. And we replace the derivative with the covariant derivative. That's like one answer. But in symplectic geometry, we don't normally have that Riemannian structure. Instead, we have a symplectic structure. And that rather intimates that we should use a different notion of a derivative. And that is that notion captured by the Lie derivative. So what's a Lie derivative is you have two vector fields. So not one, but actually two. And that's the key input. So if you want to compare two vectors, well, coming from a vector field, you're in trouble. But if you have like a reference vector field, y, then you can define a notion of how to compare two vectors. So think of y as like a reference field. And this reference field serves the role of telling you what's an allowed direction that you're allowed to transport your vector along. So on planet Earth, you know how I walked down here, I went around here, and went up here. This is solved when you have a reference vector field because it says if you're not walking in this direction, then you're walking the wrong way. So that's how, that's the role of the vector field y. It's a reference vector field. And then, once you have that, it becomes a relatively straightforward procedure to introduce a way to compare two vectors at different points on a manifold. So I'll just write out how that works. So let sigma tx and tau tx be two flows generated by x and y. Respectively. So they both satisfy this equation star. Then we're able to define a way to compare the vector x at two different locations in the manifold by using the flow tau. I think I'm going to do it the other way when I write it out, but whatever. This will be the same up to a minus sign. By using the flow to define for you the paths along which you're allowed to carry this vector parallelly. So we have that these flows satisfy the integral curve equations. Okay, just for purposes of coherence with the definition, the reference field is not going to be y. In fact, the reference field will be x. So we're going to define the derivative of the vector y. We're going to compare y at different points along the integral curve generated by x. And it turns out we have enough data to actually write down such a notion. So the way to do that is a sequence of steps, really. So first, map y at the point sigma epsilon x to the point x So how are we going to do this? Well, we know, here's the thing, right? Sigma is a diffeomorphism because by assumption this is an isotopy. We're in the compact manifold case. So we can we can find out what this vector is at x by pushing this map forward. So there's a canonical way to get a vector at x. So this is the push forward here. I know I used last week a different notation. This is the, I'll try and throughout this course stick with this notation without the D in here. I'm aware that that's confusing. So there's a way to associate canonically, once you're given this flow here, there's a way to associate a vector at the point sigma epsilon x with a vector at x. And you push forward via the inverse of the flow. And then the second step is you take the difference. Now you've got two vectors at x, take the difference if you like. And the third step is to let epsilon go to 0 and divide by epsilon. And that should give us a way to differentiate vectors. So step 1, map y at sigma epsilon x to the tangent space at x via that push forward. Then 2, take the difference between sigma minus epsilon star y and at sigma epsilon x and y at just x. And then third step is take limit of these differences. And that is a bona fide definition, derivative operation for vectors. So I have a couple of boards full of component calculations which I don't want to do now. So I think we will stop here and defer those calculations. We're going to express this whole thing in components, in coordinates, and we'll see that we get quite an elegant formula for this Lie derivative. And then we'll also extend this notion to one forms. I hope it's sort of, you can already feel how the definition will look for one forms. Instead of a push forward, we'll have a pull back. Otherwise it'll be the same. And also for mixed tensors, we'll have a way to extend this to tensors just by tensor product of this notion here. And then we'll be able to write down some Hamilton's equations on manifolds. Okay, but I think here's a good moment to stop, and so thank you very much.